know if you have any question. If we are fast to do that, then we can try to play a bit with the neural networks. There are many tools for calculating neural network. In MATLAB you have a neural network toolbox which is dedicated to neural network. You can do deep learning, whatever. I did my code for doing backpropagation. For sure it's not the best code because I did it by myself to understand what's going on. Okay? So we can use the classification toolbox, which is based with my code. But then if you want to use neural network on huge data set, it's better to go to other solutions. But before doing that, you have to really understand, okay? Otherwise, good luck. Because it's there are many things you have to deal with. So just try to get things clearer, okay? This is the structure of the neural network we have seen so far, with input, some hidden layers, and an output layer, okay? So with L is I indicate the number of layers we have. So here, for example, we have 5 layers, right? 3 hidden layers, 1 input, 1 output. N is the number of samples I have, okay? It's the number of training samples I have. And in this example, okay, for example, we have just 3 features, so 3 variables, okay, which correspond to the number of units in the input layer. Remember that neural network can really overfit the data. But when you do neural networks, it takes a long time to train the networks. So usually people do this. You have your full set of samples, okay? You have your full set of samples. Then you have your class, right? Okay? So usually people do this. You divide, you can do this randomly. You divide this set of samples in 3 subsets, which is the training set, okay? And then the evaluation set, and then the test set, okay? Then you use the training set, okay? So N is the number of training samples. You use the training set to train your network, which means to define the weights in your network, okay? But in order to train your network, you have to decide many things, which is the number of layers, the number of neurons in each layer, plus other parameters that we will see. One, I will anticipate it, is called learning rate, which is the degree of how much fast is it indicates how much fast is your network to learn things, okay? And you have to decide all these things. And it's not, it's more difficult than choosing the number of latent variables, because you know what is the number of latent variables is an integer number, and you know that if you have more than 10 latent variables, the model is going to be complicated. Here things are different, okay? And you have a lot of combinations, okay? So people what do? You try, okay? You do some trials. And how do you do that? So you try, I don't know, a network with maybe 1 hidden layer, and I don't know, plus 10 neurons plus value of the learning rate equal to 0.01. Okay? And then you try with one hidden layer but with more neurons, the same learning rate. And then you try with a different learning rate, and so on. You do many trials, okay? And how each trial requires maybe 10 minutes, 15 minutes, depending on the depending on how big is your data set, okay? Depending on how fast is your PC, but it can take some time, okay? So usually you don't do this in cross-validation, because if you do cross-validation, let's say with 5 groups, it means that you have to repeat 5 times each calculation, okay? So how do you test which is the best architecture, the best solution? You do the model with the training set, and you test with the evaluation set, okay? So you do this model, and then you see, for example, the error rate you get on the evaluation set. Okay? You can look at the sensitivities, whatever, and then you choose the solution which minimizes the error rate on the evaluation set. Right? Okay? And so then you can train your final model, your final neural network with that solution. So, for example, with 2 hidden layers, with 50 neurons in each hidden layer, and with a learning rate equal to 0.1. Let's say that this is the network giving the lowest error rate on my evaluation set. Okay? Can you see why I have to use the evaluation set? To test invalidation. Okay? But, pay attention. Now, this set of samples have been used somehow to model my data. Because I have used this set of samples, okay, to choose the best architecture. Okay? So, I need a further validation, which is the real external validation, which is what I get on the test set. Okay?
So basically the evaluation is just used to optimize the
Yeah,
okay.
exactly.
Okay.
Okay? You use it to optimize instead of cross-validation.
Okay.
Because if you want to do PLSDA with 5 cross-validation groups, calculating PLSDA takes 1 second. Here, calculating one network can take 10 minutes. So it can take days, okay, to do all this optimization. And there are, besides the number of hidden layers, the number of neurons in each hidden layer, the learning rate, there are many other parameters that you can set. So you have a lot of possibilities, and so you have to do a lot of trials. So basically when you do neural networks, you spend most of the time trying to find the best architecture. Okay? And you cannot do, with like cross-validation, because otherwise you do that, you repeat it 5 times or 10 times, it takes the whole PhD. You can get waiting for the neural networks to give you something. Okay? Okay, so these are the number of samples we use to train. Okay? Okay, layers. This is the number of neurons in each layer. Okay? Then we say that if we have a multi-class problem, okay, so let's say we have 4 classes, then we have in the output layer 4 neurons, 1 for each class. If we have a binary classification, okay, we just need not 2 but 1 neuron, okay? Because it's 1, 0. So we can just use 1 neuron in the output layer, okay? Okay. So let's see. Now, here, I mean, if you remember support vector machine, you had a optimization function, and then support vector machine find the best set of coefficients that minimize that optimization function. Okay, and if you remember, in that case, the optimization function was taking into account the margin between the two classes. Okay, here we have still here a new function, okay, to be optimized with neural networks, and so we will have to find the set of weights, not coefficients, but here we have a lot of weights, okay, inside the network that minimize the cost function, this objective function, which is very similar to what we have with the logistic regression. Okay, so this is the cost function with the logistic regression. Okay, which is a very simple model where you have a linear combination of your variable, and this is the function that we use, okay, in each node, in each neuron, okay, of our network to send the information, okay, from one layer to the other one. Okay, this is the function. And this is the optimization function. What does it mean? What you try to do, okay, is to minimize, okay, these two terms, and again you have here something. Do you remember? This is very similar to support vector machine. This is a regularization term, okay, with the coefficients for the logistic regression, and these terms, on the opposite, it takes into account how good is the prediction, okay? Let's say that y, okay, here can be 1 or 0, okay? So let's say that, let's do a simple example. You have binary classification, so you can code your class as 1 or 0, okay? So if you look at this function, you try to find the coefficients, okay, which have very high linear combination for class 1, much higher than 0, and very low linear combination for class 0, okay, much lower than this threshold, okay. This is the meaning of this. Can you see that? Let's say that my sample belongs to class 1, okay? I want this linear combination to be very high. Why? Because this function, the logistic regression function, okay, if the linear combination is very high, is very close to 1, okay? 1 means that this term goes to 0, because this is equal to 1, okay? And here I have the log of 1, which is 0. So I minimize this function. Okay? The same when you have a sample in class 0, in the other class, you want this linear combination to be very low. Okay? Because, look, this function, when the linear combination is very low, is negative. Okay? This function is equal to 0. Okay? So, now the class label is equal to 0, so this term is equal to 0. Here you have 1, and here you have the log of 1 minus 0, which is 0. Okay? So you find the coefficient that minimizes this stuff. Okay, when you do logistic regression. Here, of course, if you want to do neural networks, things get a little bit more complicated. Okay? Because now you don't have a single function like in logistic regression, but you have many, okay? So the cost function of the neural network, which we try to minimize, okay, is this one. So we try to find the set of weights. Okay, now we do not speak about coefficients because we have weights, which are the coefficients of all the linear combinations you have in the neural network. We try to find the set of weights that minimize this stuff. Okay, where you have again something which is similar to the regularization term we had before here. Okay, this is the sum of all the weights you have in the network. And again here this is related to how good is the prediction you get, okay, between the output of the network and the actual class. Okay?
Could you rephrase it? I'm a bit lost.
So this is the cost function which is minimized. Okay, so neural networks, okay, find the set of weights. Okay, this is what we have to do. Okay, we have these weights that each of these arrows is one of the weights. Okay, this weight, all the weights govern how the information, okay, is propagated. Okay. At the beginning, these weights are random, and we have to find, okay, a suitable value for all these weights. How? By minimizing this function. Okay? Where you have these two contributions. Okay? Here, if you look, okay, this is the this part is related to how good is the prediction you get as output with respect to the real class. Okay? So you remember if you have two classes, 1 and 0, okay, you want samples of class 1 to get an output which is very close to 1.
Isn't it kind of sensitivity?
No, because it's quantitative. Okay?
Okay.
So you get values, okay, in between 0 and 1 as an output.
Okay.
But you want samples of class 1 to have values close to 1, and samples of class 0 to have values close to 0. Okay? So you try to minimize this stuff. It's a kind of residual. Okay? It's a residual. Okay? Plus this regularization term, okay, where you have the weights, which is similar as a meaning to what we have seen with the super vector machine, where we had the coefficients. Okay. So okay. So all this part, okay, you can simplify, okay, looking at this equation, okay. So here you have the log transformation, whatever, but minimizing this stuff means minimizing this one, where these are the residual between the true class and this is the output, okay, of the network for that sample. Okay? So if my sample is in class 1, I want the output to be very close to 1, so the residual is very small. If my sample is in class 0, I want the output to be close to 0. Okay? 0 is perfect or close to 0. Okay? So we try to find the weights which minimize, okay, these residuals. So the approach, of course, is supervised, okay? Because we need to know the class labels for our samples. Okay. So now let's see how this process goes, okay? And then I hope also to clarify what we have seen, what we have said this morning about the samples and how do you present samples, okay? But, okay, then we will see what happens with the full data set. But just to start, okay, imagine to have just one sample, okay? So, you have the first sample. So you have the vector x, which collects the variables, okay? This will go as input layer. And then for the same sample, you also know, I mean, this is a training sample, so you also know the class labels, okay? If you have two classes, this is not a vector, it's just one scalar value, okay? Or 0 or 1. If you have more than two classes, then this is a vector, okay? So you have this sample, and if you remember, first we apply forward propagation. So it's what we have seen this morning. So if you remember it, it's just the same, exactly the same procedure. So we have the input layer, which is our sample, okay? Then we get, for each of these neurons, we get a linear combination of the input layer and the weights, okay? Which govern this connection between input and hidden layer. So do you remember we have a matrix of weights? This is the linear combination between the input layer, okay, the sample, and these weights, okay? So we get this linear combination, we can call them Z, and then we apply the, you remember, the logistic regression, okay, the function which is the logistic regression. And what we get is the activation in this second layer, right? Is what we have seen this morning. Then do you remember what happens? We go from here to here. So we will now use this activation as input variables, okay? We will use all the weights here. So we will get the linear combination between this activation and the weights. Then we will use the logistic function to get this, the activation in the third layer, which is the second hidden layer, okay? So we do this, okay? We take these values, okay, the activation in these neurons. We have the weights. Okay, now the weights are random numbers, okay? Because we have to initialize the weight. We need some weights, okay, to start. So they are random numbers in between 0 and 1. Okay, we go. And we get the linear combination, then we apply the logistic activation function, okay? And we get this, okay? Of course, then, I mean, now here, I didn't put the bias because otherwise it was too much complicated. But of course, then you have also to add the bias, okay? And then you can imagine now what happens, because here we do the last step of the forward propagation, okay? So we go from the layer number 3 to the last layer, number 4, which is the output layer. Then, of course, we have to stop, okay? Again, we do exactly the same. So, this is the linear combination of this activation function, okay, and the weights which connect the hidden layer number 3 and the output layer. So we do the linear combination, and then we apply again the logistic function, okay, and so we get the output layers, okay. So, or better, we get the activation in the output layer, okay, which is actually the output of our neural network. Okay. Now, let's say we are doing a multi-class specification. Okay, we have 4 classes. These values will be values in between 0 and 1, okay, because it's the output of the logistic function. Of course, if my sample belongs, if this sample belongs to class number 2, okay, I want this output to be close to 1, and the others close to 0, okay? Of course, at the beginning, we will not get that, because we have random weights, so there will be a lot of mess in the network. But then the network is able to organize the information, okay? How? So, we have finished the forward propagation, okay? And now we have to, on the basis of these outputs, okay, we have to go back with the back propagation, okay? So now we start the second phase. So we go back with the backward propagation. And on the basis of the residuals we have here, okay, we will update the weights. This is the idea, okay? So let's say that the sample belongs to class 2, okay? And let's say the outputs are exactly 0, 1, 0, 0. That means that the network is perfect, okay? So the weights will not be updated because it is already doing well, okay? While on the opposite, if here you have high residuals, okay, then the update will take place, okay? And we will change the weights in order to better predict the outputs, okay? How? Everything is based on derivatives of the activation function. We will see it in the next slide. But actually what you do is this stuff. So you calculate a delta term, which is the error, okay, you get in the output neurons, okay? So for each of these neurons, you can define this stuff, okay? Which is what? This is the difference between the activation value for that neuron and the true class label, okay? It means that if these are equal, then we do not need to update anything, right? But if we have a residual, that means that my class is 1 and the output is 0.5, so we have a residual, then we will get an error, okay? This part, okay, is actually the derivative of the activation function, okay? This is the activation, this is the value of the activation function for this neuron, okay? And this is the derivative. What does it mean? Can you see? This is the activation function, do you remember? Oh, okay. And this is the derivative. It's derivative, okay? It has a maximum here, where you have, how do you call it in English? I don't know, less. Can you see the derivative here for this function? Okay. So, what does it mean, this stuff? That you somehow leverage the error you get on the basis of this. Okay? You want this to be very small, right? So it means that you don't want your prediction, okay, to be here, close to 0. Okay? But you want to have linear combination which have very high or very low values, because there the derivative is 0. Okay? It's the same, you remember before with the logistic regression, we say that what you want is to have a linear combination which are very high or very low. Okay? It means that think that this is a kind of threshold. Okay? If you get a linear combination which is equal to 0, which is the output of the logistic regression function, 0.5, okay, which we we do not like, because it means we don't know in which class we want to predict that sample. Okay, so we want to. This derivative means that we want to avoid to have solution here. Okay, and so we use this derivative here to calculate this delta term, which is the error. Okay, that we want to take into account. Then we do this for all the neurons, okay, we have in the output layer. So if in the output layer we have 4 neurons, we will have 4 delta values. Okay? Now here it's expressed in terms of vectors, but this is exactly what we have seen before. Okay? Before we have seen it just for one single neuron. Okay? This is just for all the neurons. Okay? So it's a vector. It's a vector calculation. Okay? So again, we get these delta values for the output layer, one for each neuron. Okay? This is the difference between the activation function and the real class. Okay? And this is the derivative. Okay? As we have seen before. Then the idea is to now go back. Okay? So you do back propagation. So in forward propagation you start from here and you go to from the input to the output. In back propagation you go from the output layer not to the input, but you stop here. Okay? It makes no sense to update the samples. Okay? So it's a process which starts from the right and goes to the left. From the output layer until the first hidden layer. Okay? How? In this way. So this is what we got before. Okay? Looking at the error and the residuals. Then we use this information, these delta values. Okay? And with the weights, do you remember these are the weights between this layer and this layer? Okay? We do a linear combination of these weights and the delta terms, and again we take into account the derivative, okay, of the activation function. Of course, with respect to this, okay, with respect to the activation functions of the third layer, okay, which is this one. So from here we go back. And this means that we get some delta values, so errors, also for these neurons. Okay? For example, here we have 1, 2, 3, 4, 5 neurons. So we will get a vector with 5 dimensions, which are the errors associated to each of the neurons. Okay? And then, again, from here, we go back another step, exactly in the same way. So now we will get the delta values, okay, for neurons in the second layer with a linear combination of the weights in between these two layers, then the delta values we got before for the third layer, and the derivative of the activation function in the second layer. Okay, it's exactly the same process. And we go back. Okay? I mean, can you see from the beginning that if the neural network is okay, so what the output is exactly the class equal to the class, then these are 0, these will be 0, these will be 0, so there is no update. Okay? So once the network can get a good result, then you don't have, okay, an update on the weights. I mean, so you will have a lot of course at the beginning the weights are random, so you will have a lot of corrections. But then this correction will be smaller and smaller and smaller. Okay? Because actually you do this process many times. Okay? So you do forward and then you go backward. This is one iteration. Then you do that again. Okay, but now the weights have been changed. We will see how. But the weights have been updated a bit, okay, on the basis of the information, okay, we get. So then you do another iteration, forward and backward, forward and backward. And the more time you spend, the more this correction will be small. Okay? It's exactly as the learning of a child. Okay? So you learn a lot at the beginning. Okay? So in, I don't know, in the first 2-3 years, you learn how to eat, how to work, how to speak. And then, I mean, this learning is always smaller, smaller, and smaller. Okay? After your PhD, then you don't